Welcome to the deep dive. So, you've sent us this fantastic collection of notes from the GenWise Educational Camp.
Yeah, quite a stack.
And our mission today really is to pull out the most fascinating bits, the insights from those days. Think of it like getting the highlights across a whole bunch of subjects from, well, model planes to AI.
It really is an impressive mix. You've got aeromodeling, AI and ML, economics, maths, neuroscience, pathfinders, storytelling, submarine design, 2 feet of science, and wired wonders. It's like a whirlwind tour.
Exactly. And we're not just listing things. We want to synthesize it all. See what these, well, seemingly different activities tell us about learning itself.
Like what are the common threads, the core ideas that keep popping up?
Right. And where do these fields maybe connect in surprising ways? We've definitely seen some interesting patterns already just looking through your notes.
Oh, absolutely. Get ready for a few of those aha moments, I think, because we see how these things weave together. You start to see how, different activities are often exploring similar fundamental concepts.
And for you, our listener, if you want to get up to speed quickly without getting bogged down, we've tried to make this really clear, engaging. So let's dive right in. Maybe start with aeromodeling. High-flying insights.
Sounds good. So your notes from day 2 of aeromodeling, they show this great mix of theory and practical application.
Okay.
So it wasn't just building something. They really dug into the simple machines involved, even the physics behind collisions. Applying theory like that, right away, it makes abstract stuff so much more real.
Right. And then they took that understanding and applied it directly to the RC plane's electronics. And we're talking the guts of it, The BLDC motor, the ESC.
The electronic speed controller, and the XT60 connector, the receiver, the transmitter parts.
It's like taking apart a complex gadget to see how it actually ticks at the most basic level.
Exactly. And they taught a really core skill, too. Soldering. Yeah. Sounds simple, maybe, but physically connecting components, that's crucial in so many tech fields. Plus, they talked about lithium batteries, how to charge them, very relevant today, touches on chemistry, safety, practical stuff.
Okay, that makes sense. Then day 3 seems to have connected more dots, linking things like volume, pressure, temperature back to flight.
It did. And that's the kind of link that makes physics principles really click, when you see them in action. What's really interesting is how they explored Archimedes' principle. We usually think of it for like boats and water, right?
Yeah.
But the exact same ideas explain how air gives lift to a plane. It's a really neat example of how fundamental physics just works across different areas.
And the paper plane experiment sounds brilliant. Not just holding and throwing, but actually structured.
Totally. Designing different features, winglets, different nose shapes.
Okay.
Making predictions, testing them, analyzing what happened. That's proper scientific thinking right there.
That whole cycle. Predict, test, analyze. That's science in a nutshell.
Exactly. It mirrors the real scientific method. And then they got into specifics, like servo versus BLDC motors, how they work differently, essential stuff for mechanics, electronics.
Right.
Plus, they even touched on airfoil design, different plane configurations, giving them a peek at the more advanced side of aerodynamics.
Okay, so moving from the physical world of flight to the digital world of algorithms.
Yeah.
Let's look at AI and ML. Day 2 seemed to lay down some key foundations.
Yes, absolutely. That basic difference between traditional programming and machine learning seems like a big early point.
You mean how ML learns from data instead of just following pre-written rules?
Precisely. It's data-driven learning. And the process, data collection, training, testing, that's the core loop. Your notes mentioned a really hands-on exercise, classifying data, actually drawing lines on Colab notebooks. That sounds like a super intuitive way to get how a machine learns to separate things. Makes it less abstract.
Yeah, tangible. You can literally see the algorithm trying to find the best dividing line.
Exactly. And the fact they use GenAI to improve the instructor's own notebooks. That's an interesting twist, isn't it? Using AI to help learn about AI.
That is clever. And the focus on real-world problems, using open-source data sets for projects, that makes it immediately relevant.
Totally bridges theory and practice. And the professor's example, the speech-to-text for Marathi kids learning multiplication, that's a fantastic illustration of the actual impact ML and GenAI can have.
Yeah, using tech to solve a specific need, make learning easier. That's powerful.
And it sounds like the students quickly got why data preprocessing matters when they hit imperfect data.
The real world isn't clean and tidy.
Exactly. Learning that you need to clean and prep data is a huge practical lesson in ML.
So day 3 went into more specific methods, like logistic regression.
Right. Introducing a specific algorithm lets you go deeper into the mechanics. and understanding things like cost and loss functions, basically, how you measure how well the model is doing, and optimization. That's key to refining them.
Like tuning an engine, sort of.
Yeah, or tweaking a recipe, like you said. You're aiming for the best result. The notes say students really grasped gradient descent intuitively and asked good questions. That suggests they were really engaging with it.
Active learning, not just listening.
Definitely. And using Gemini to write code, but then encouraging them to debug by asking the AI why it wasn't working. That's teaching problem solving, not just coding, learning how to learn with AI.
That's a crucial skill now. And the fun examples like house birds prediction or thinking about helping their parents makes it relatable, shows the potential impact.
For sure. Okay, switching gears. Let's look at economics. Day 2 focused on some really core principles, it seems.
Yeah, incentives, right. And how important it is to get them right. That seems fundamental. Understanding how they drive behavior, sometimes in ways you didn't expect.
It's so true. Poorly designed incentives can backfire spectacularly. And then the idea that trade benefits everyone involved, plus specialization, division of labor. These are the basics of why economies even work, how exchange makes us better off.
The win-win of voluntary exchange. And the quick civics bit, state, nation, country, and students finding examples, that's building foundational understanding of our societies.
Exactly. And thinking at the margin, the cost or benefit of just one more thing, that's a powerful decision tool, not just in economics, but, well, everywhere.
Uh-huh.
Right.
Like the debate mentioned on government intervention in poverty or crime, applying that marginal thinking to big social issues.
Right. And clarifying democracy versus republic, another key piece of civic literacy. Then day 3 built on that with more nuance.
Opportunity cost what you give up, that's a big one.
Critical for seeing the real trade-offs in any choice. And breaking down transaction costs, the effort of searching, bargaining, and forcing deals that gives a much richer picture of economic activity.
Right, it's not frictionless. And sunk costs, the sunk cost fallacy, learning when to cut your losses, basically. That's a life skill.
Hugely valuable, and clearly separating price, value, and cost avoids a lot of common confusion. But maybe the biggest idea that day was the law of unintended consequences.
Ah, yes. The reminder that actions can have ripple effects you didn't foresee.
It's so important. It argues for careful thought, maybe a bit of humility, when making changes, whether it's policy or personal decisions.
Definitely. And framing change through those 3 agents, government, society, markets, gives a useful lens for analyzing how things evolve, understanding their different roles.
Essential for a full picture. Okay, let's pivot to mathematics. Day 2 looks like it tackled some real bedrock concepts.
It does, building up the number systems, naturals, integers, rationals, and showing why we need each new type. Because they let us solve problems we couldn't before.
Exactly. It wasn't just arbitrary invention, it was necessity. You need integers for subtraction, rationals for division.
Right. And the idea of sets, making new sets by adding elements, that's how mathematicians build new structures, isn't it?
Fundamentally, yes.
Yeah.
And equivalence relations, partitions using that mod 5 example. Sounds abstract, maybe, but it's a powerful way to group things by shared properties. Super important in higher maths.
Okay. And generating a new structure like S by adding con, that shows how you can actually expand the world of numbers.
Precisely. Then they got practical with the Euclidean algorithm for finding the greatest common divisor. A classic, still incredibly useful.
And Bezout's identity. Expressing the GCD is a combination of the original numbers.
Yeah, that's not just neat math. It has real uses in cryptography, computer science, and solving modular equations remainder problems, another key skill with computational applications.
So modular arithmetic is like a whole different number system based just on remainders.
Pretty much. It's a shift in thinking that opens up new possibilities. And finally, even sketching Euclid's proof for infinite primes, that's a taste of pure mathematical elegance.
Beautiful stuff. Day 3 then built on that number theory foundation.
It did, exploring some really interesting extensions and uses.
Like how solving equations where a product is 0 works differently in modular arithmetic compared to regular integers.
Exactly. That fact you can multiply 2 non-zero things and get 0 mod some number is a crucial difference. And revisiting Bezout, then introducing Blankenship's method that shows the evolution from a core idea to a more efficient way to calculate it.
And going over Euclid's proof again reinforces its importance.
Definitely. Fermat's little theorem using that colored bead necklace analogy sounds like a really smart way to make it intuitive.
Yeah, visual explanations can really help with abstract stuff.
Absolutely.
Yeah.
Helps grasp why LPP is divisible by prime p, and showing how it can quickly spot composite numbers. That's a powerful application.
And the quick proof for infinite Pythagorean triples fun shows there's endless patterns even in simple relationships. And proving root p is irrational for prime p, a classic result showing the complexity of real numbers.
Right. Then the binomial theorem, basics combinations, symmetry essential tools for algebra, probability, and connecting it all to abstract algebra through symmetry, rotations, reflections. Thinking of those as having a kind of multiplication, that's a great doorway into more advanced math.
Okay, from abstract math to the very physical brain. Let's look at neuroscience. Day 2 seems focused on basic structure.
Yeah, and that 2D brain sketch, that's great active learning. Drawing it helps you remember the parts. And the idea the brain doesn't inherently know itself that frames why we need neuroscience in the first place.
Good point. Studying neural circuits, different neuron types, that's foundational. And the knee-jerk reflex example makes a simple pathway really clear and relatable.
Totally. And neuropictionaries sounds like a fun, engaging way to learn potentially tricky terms through visuals.
Makes sense. And then action potentials, chemical and electrical gradients, getting into how neurons actually fire and communicate.
The core mechanisms. Day 3 seems to have reinforced that and gone a bit deeper.
Like filling in the brain models they'd sketched.
Exactly. Solidifies the learning. And continuing neuropictionary suggests it worked well for retention.
More neural conduction action potentials, fleshing out the details, and looking at brain wiring in clinical cases. That links the biology to real human conditions.
Fascinating area. And finally, detailing how messages cross the synapse, the role of neurotransmitters that explains the actual communication network.
Crucial stuff. Okay, shifting now to Pathfinders, this seems all about information skills for the modern age, especially using AI tools. Day 2 focused on LLMs.
Yes, and the emphasis on detailed prompts is spot on. Role, audience, instructions, constraints, getting specific is key to getting good results from an LLM.
Right. Garbage in, garbage out still applies, even with AI. And using one LLM to generate prompts for another, that's a clever hack.
It is a good way to refine your thinking. Plus, cross-checking outputs between different LLMs, that's smart practice for catching potential errors or biases, building reliability.
Good point. Then they broke into teams to research and prep questions for a speaker. That sounds like solid practical skills development.
Very much so. Collaborative research, preparing for a real interaction, and learning to produce reports in different formats, short and punchy versus detailed. That's a vital communication skill everywhere.
Definitely. And the journaling for self-reflection helps them think about how they learn and improve.
Exactly. Day 3 moved into models of change and more advanced research techniques.
Like the stages of life and change model.
Yeah.
Uninformed optimism to success.
Yeah, it provides a framework for understanding the journey of learning or tackling something new. Often involves hitting roadblocks.
True. And researching someone using deep research features of LLMs. That's learning cutting-edge online investigation skills.
Very practical. Then taking that deep research and boiling it down to a one-pager for different audiences again emphasizes tailoring your communication.
Adaptability.
Right. And the big takeaway, good research leads to better conversations with experts. Preparation pays off.
Makes total sense. Okay, let's switch to storytelling. Day 2 seems packed with foundational narrative techniques.
It does. Active versus passive characters who drives the story. That's fundamental. And the types of conflict. Public, private, personal.
No.
Building layers.
And sequencing conflicts based on stakes. That's all about managing tension, keeping the audience hooked, and fear as a motivator for growth, using Batman as an example. That's a great way to explore character arcs.
Really insightful.
Yeah.
And that principle, good guys get lucky once, bad guys get lucky all the time.
Yeah.
It sounds cynical, but it's about creating dramatic obstacles for the hero, right?
Yeah, you need challenges. And disaster versus crisis, the element of choice in a crisis being key, highlights character agency.
And the black-white-gray characters discussion, including that student's question about connotations, shows nuanced thinking about character depth and potential interpretations.
Good that they address that. And the pullback technique, planting seeds early for later payoff, that's sophisticated writing.
Creates that sense of inevitability or surprise done well, and the absolute necessity of character change that's core to most satisfying stories. They have to evolve somehow.
Right. Establishing a time clock for tension, classic technique. And using Ford v. Ferrari screenplay and scenes provides concrete examples.
Yeah, seeing it applied makes the principles stick. Day 3 was then about actually doing it. And more craft tips.
Students writing their own stories, using the tools, that's where the real learning happens.
Definitely. And discussing sentence length variation, referencing Gary Provost. That's getting into the musicality of prose, the rhythm. Important stuff.
In Hemingway's 7 Tips, concise advice from a master. Plus, using Lapata Lady's screenplay and scenes more practical examples.
Keeps it grounded in real narratives.
Oh.
Okay, from stories to engineering. Let's dive into the submarine deep dive. Day 2 sounds very hands-on.
Extremely. Building the actual circuits, LEDs, resistors, capacitors, the ESP32 microprocessor, making electronics tangible.
And more soldering practice. That student's quote about the motherboard transforming really captures the magic of building something complex.
Yeah. Installing Thani for coding and then seeing their code actually make voltage appear on the microcontroller, that must be a huge aha moment.
Oh yeah, connecting the abstract software to physical reality. The analogy comparing computer parts to submarine functions probably helped make input-output concepts clearer too.
Makes sense. And starting with just blinking LEDs, a classic first step in hardware control.
Is simple but effective. Day 3 continued the build and got deeper into the coding.
Setting up the Thani IDE, right? And using PWM pulse width modulation to control LED brightness. That's a step up in control sophistication.
Allows for more nuance than just on-off. And using MicroPython, basic commands like while loops, fundamental programming concepts applied directly. Understanding the relays function, another key component for controlling power.
And again, more soldering. Plus understanding the motherboard, how the subcomponents fit together, getting the whole picture.
Holistic engineering view. Right now for 2 feet of science, grounding us in fundamental physics. Day 2 started big, with the scale of the universe.
Yeah, that 10-kilometer paper analogy really puts things in perspective, and framing it around why and how things move gets right to the heart of classical mechanics.
Using Galileo's thought experiment introduces the power of reasoning. Then defining force, different types, building the basic vocabulary.
Newton's first law, inertia, key idea that objects resist changes in motion. And clarifying that constant velocity is motion without net force, not just being stopped.
That's a common stumbling block. The ball in the plane example is perfect for illustrating inertia. And mentioning microgravity on the ISS gives a real-world, near force-free context.
Good examples. And emphasizing forces, our vectors' direction matters. They don't just add like regular numbers. Distinguishing speed from velocity to scalar versus vector. Crucial distinction.
Absolutely. Day 3 then got into applying these ideas.
Adding vectors on graph paper. Hands-on way to see equilibrium and resultance. And distance time, velocity time graphs, essential tools for visualizing and analyzing motion.
The match the graphs activity sounds like a good way to check understanding. Then defining acceleration, the rate of change of velocity, the next key concept.
And tackling that tricky idea that acceleration and velocity can be in different directions, like when braking.
Clarifies a common point of confusion. And answering why doesn't the moon fly off? Great lead-in to gravity.
Newton's second law, TAPMI. The core quantitative link between force and motion. And finally, the universal law of gravitation, every mass attracts every other mass, fundamental force of nature.
Exactly. Okay, last one. Wired wonders. Practical electricity and circuits. Day 2 was hands-on with tools and basics.
Looks like it. Using multimeters right away, essential skill. Measuring resistance of different resistors makes that property tangible.
And a hand resistance experiment, dry versus wet. Observing resistance drop with moisture. That's a brilliant, memorable way to show why electricity and water are dangerous together.
Visceral lesson. The water pipe analogy for resistance is a classic too. Helps visualize current flow being impeded. And explaining Ohm's law, VIR, with everyday examples makes it stick.
Definitely. Highlighting the multimeter's versatility, voltage, resistance, current shows why it's the go-to tool. And explaining parallel versus series circuits, how current and voltage behave differently in each. That's absolutely fundamental circuit theory.
Right. Conventional current direction needed for reading diagrams. Energy and power concepts, PVI, watts, connect electricity back to broader physics. And calculating power in their own circuits makes it active learning.
Ties it all together. Day 3 then sounds like a specific circuit challenge.
Yeah, building a circuit with a 9V battery, resistors, breadboard, aiming for a specific 3V drop across one resistor. That's applying Ohm's law and circuit rules directly.
Great problem-solving task. And reinforcing the rules. Current splits in parallel, voltage stays the same across parallel branches, voltage drops across series components, current stays the same through a series path.
Got it. Using the multimeter to check voltages verifies those rules. And using Ohm's law again to calculate current reinforces the VIR relationship.
Then introducing diodes, one-way valves for current, and LEDs as light-emitting diodes needing the right orientation and a current-limiting resistor. important components.
And that student observation LED burning out when connected directly to 9V, that's instant understanding of why the resistor is crucial, learning by, well, almost breaking something.
Sometimes the best way. And the water tank analogy for the diode reinforces its one-way function. Let's visualize it.
Wow, okay, that was quite a tour through everything. Looking back across all these GenWise notes, some really strong themes just jump out, don't they?
They really do. One big one is definitely that constant back and forth between theory and actually doing something, hands-on application.
Yeah, it wasn't just listening. It was building, experimenting, designing, even simple things like paper planes. That active experiential stuff seems key.
Absolutely.
Yeah.
And the importance of, experimentation, observation, analysis that came through everywhere. Testing designs, classifying AI data, troubleshooting circuits.
It's not just learning the rules, it's seeing how they work, testing them yourself.
Right. And what's really cool is seeing those fundamental ideas connecting different fields. Buoyancy in subs and planes, math underlying physics and computing. It really shows how knowledge isn't just in silos.
It's all interconnected. And beyond the subjects themselves, it's clear they were building crucial skills, problem solving, critical thinking, debugging code, optimizing designs, analyzing results. That's thinking analytically.
Definitely. These specific activities, they really touch on fundamental concepts relevant everywhere. Incentives from economics, clear communication from pathfinders and storytelling, laws of motion from physics. These are just tools for understanding the world.
So thinking about this incredible range, maybe for you, our listener,
Yeah.
what connections do you see in your own work, your own interests? Or maybe the challenges you're tackling right now?
Yeah, and which of these learning styles, the hands-on, the inquiry-based stuff, resonates most with you? How could you maybe apply that to your own learning?
Something to think about. We really hope you'll reflect on all this and maybe dig deeper into anything that particularly caught your interest. Learning's always an adventure, right?
It certainly is.
Well, thank you for joining us on this deep dive through your GenWise notes. We hope it gave you some valuable insights, maybe a few of those aha moments.
I'll go too.
Until our next exploration.